Okay, Assalamu alaikum and welcome to this session in which we are going to do some um, hands-on with the restricted Boltzmann machines. Before going into these hands-on activities, so we're going to just do a small primer. That primarily what we're looking at in the RBM is that we have a layer of hidden units, and we have a layer of visible units. And what we're supposed to do is to actually give the input data here. And that input data is going to go to the hidden layer through the normal feed forward method. And the hidden layer is primarily going to generate new data, which should be very close to the real data which is being input at layer B. So in order to do this generation, we use the concept of an energy function. Energy function is a concept which is derived from physics to measure the energy of a system or the configuration of the system at any given time stamp. In the case of restricted Boltzmann machine or the Boltzmann machine in general, we are actually using this concept of energy to estimate the probability density or the joint probability density, which is H, V. As we all know that it is not possible to sample directly from the joint posterior. So what we will do here at this point, in order to help the hidden layers generate the new data, we are going to use the concept of Gibbs sampling. And we all of us know that Gibbs sampling basically works on conditional probabilities. So if I have to estimate, for example, probability of X, Y, then first of all, I can estimate, let's say, probability of Y given X. I can sample from this distribution. From this, I can get the value of Y. And then I can use this Y to get the value for X through the other conditional distribution. So in this way, I can have multiple X, Y pairs, and which are equivalent to the probability which is attained here. So in this way, I can sample from the posterior distribution directly. In this way I can estimate the joint PDF or the joint posterior through the concept of Gibbs sampling. Similarly, I will use when I input the data from the input layer to the hidden layer. So I'm going to sample from primarily H equals to 1 given X or given V, for example. And H equals to 1, I'm going to estimate this for each of the neurons in the hidden layer. And when I come back down, so I'm going to sample from probability of V equals to 1 given the vector H, which has been already sampled from here. So that is the basic algorithm that we are using to generate the data. So we are sampling from the conditional distributions. In fact, 2 conditional distributions in each iteration to get the generated data. So that is the basic concept that we are using here. And the contrastive divergence algorithm of the Boltzmann machines basically requires us to make certain iterations of this. So once I input the data, so let's say I first input the data, then I sample from this conditional, and then I sample from this conditional, and I can repeat this process several times or k times. And then, what comes here, I will just take the last sampling probability of H equals to 1 given V, and that is going to end my iteration. Typically, the value of contrastive divergence, which works very well, is C equals to 1. So I just need to have one loop. So I send the data, sample from this distribution, then I sample from this distribution, and then I sample from this distribution again, and that is it. But if I want to have the value of 2, so then I'm going to input the value, sample from this distribution, come back, then sample here, come back, then again sample one the last time. So it basically, this is the one iteration. I go up, I go down, and then I go back up again. So that is one iteration of the Boltzmann machine or the RBMs. So the only difference between Boltzmann machines and the restricted Boltzmann machine is that In the Boltzmann, in the RBMs, the connections between the neurons in a single layer do not exist. So that's the assumption. That's why they're called restricted, and that helps me analyze each neuron of each layer independently. So take the joint, estimate the joint PDF based on the individual distributions of each neuron or the independent distribution of each neuron, because I'm assuming there is no correlation between the values or the neurons in one layer. So these are some of the basic concepts regarding the RBM, and each state is represented by a particular H and D combination. That is the configuration of the system. And if the system has more energy, if the energy is very, very high, then basically that means I am still not generating the true data. So my energy is high. There's a lot of confusion between the hidden layer and the visible layer. So I need to work harder on this. So I need to train the system more in order to reduce the energy. So if the system has less energy, then that means basically if the system has less energy, then that means I'm close to convergence. So my job is to minimize the energy. So by estimating the joint PDF through Gibbs sampling, so I can minimize the energy, and then after every batch, I can update my weights and biases accordingly. So as far as the weights and biases are concerned, so I just have one weight vector, which is consists of all the connections that lie between the two layers, and the weight vector here, and I have the bias vector for the hidden layer, and the bias vector for the visible layer. So there are two different bias vectors. So that's all I have to estimate. In order to update the weights and biases, I use the direct difference between the original input and the generated input. Generated input is the input which is coming from this layer. So I use the direct difference to update the biases. And in order to update the weights, I'm using this difference as well as the gradient. So I'm using both these techniques basically to update the weights. So in order to for the weight update, I'm also using these conditional values. So that gives you an idea of the joint distribution, because the weight is the actual matrix that needs to be done. And for the biases update, I'm just using the simple V0 minus VG. Okay. So that's some of the basic stuff that we covered in the class today. Although this has been pretty brief, so now let's move to the hands-on. So the first example is a famous example. So in this example, I have a set of users who have rated movies that they have watched. So in total, the number of movies that we have is around 3,500, and the total number of users is around 6,000. And the other data is regarding the rating. So in this, we are using the PyTorch library, the neural network library, to implement the RBM. So I just read the 3 data sets. The data set is available online, so you can search for that. There are no headers here, and the separator is double colon. So this is some of the sample from the movies file. You can see that we have the movies, and they have some sort of a classification. So in this case, the idea is I am presenting the vector here, the rating vectors here, that the users have provided ratings to the movies. So I'm just putting the rating vector here. So every user's rating vector will be input at the visible layer, and my idea for the hidden layer is that I can classify the preference of the user according to the type of movie that is. For example, this can represent the sci-fi, this can represent a horror, and this can represent a comedy. So if the user is more into sci-fi and horror, then there's more chance in the joint PDF that these two will fire for this particular user. And if a user is into comedy more, So when I input the data for those users, then there's a chance that this will fire more and these two will not fire that much. The probability of them firing is less than the probability of this neuron firing. So that's the intuition behind the use of RBMs in this case. So you can see the user data. The user data is like, this is the user ID, this is the gender, this is the age, and this is, I think this is the movie number. So these are user data, and then we have this ratings data. So this is the user, this is the movie, this is the rating. So rating is between 1 to 5, where 1, 2 are considered as bad ratings and 3, 4, 5 are considered as good ratings in our problem, because we have to convert the problem to a Boolean scenario. So this thing here is the timestamp. So we just read the training and test set from this file, and then we just convert them to arrays. So these are some of the things, the training set file and the test set file, obviously. So we can see that we have the 943 users have watched movies, and they have watched total 1,682 movies. So this function is basically used to convert. This function is used to determine which users have watched which movies and provided ratings for which movies. So we are just in this function, we are just only getting the data for those users who have provided ratings after watching movies. So we are just getting that. So this is just one snapshot of ID movies. That this is one user of the last user, in fact, who has watched all these movies and who has provided ratings for these movies. And these are the ratings that he or she has provided. So we implement a separate ratings vector according to the data in ID movies and ID ratings. And then, just the last one, we implement this. And the length of training set is this one, and the number of instances that I have, I think these are the number of users that I have, 1682. Oh, in fact, these are the number of users. This is the number of movies. So first of all, I convert both the training and test sets to the float tensor, which is a multi-dimensional matrix in Torch. So it becomes like this, like an NumPy array. And then I do the discretization that if the rating is 1 or 2, then I'm giving 0, because that means there's a bad rating. Otherwise, I give 1. And I do the same for the test set. If there is no rating, then we give it a -1. So it's all Boolean now, -1, 0, 1. So obviously, either it will be 0, 1, or it will be just -1 for any given value. So this is the class for RBM. So in the constructor, I'm just initializing the number of neurons in the visible layer and number of neurons in the hidden layer. And I'm initializing them all based on the standard normal distribution, the weights and biases. And this is the first function, which basically is used when we are going from the visible to the hidden layer. So this is a probability of H equals to 1 given V. So for that, I'm just doing the feed forward. So I put the input, I make the matrix multiplication, I calculate the activation, I give that to the sigmoid function, and then I give that to the Bernoulli function for sampling based on the Gibbs distribution. So I get P H equals to 1 given V. So obviously I'm using the Bernoulli because I'm working with the hidden layer always works with Boolean variables. And similarly, this is the function P of V equals to 1 given H. So in this case, I do the feed forward while going down. So I calculate the total, then I calculate the activation, then I give it to the sigmoid function, and then I do the same Bernoulli mapping here. Then the train function is implemented as the difference between the input data and the difference between the acquired data primarily. So that's what we find the difference between them. And I'm using the conditional probability here, and the conditional probability here. Here it is V given H, and here it is H given V. And so in this case, we have to update the weights, to update the biases. I'm just using the difference directly. That's the case here. To initialize the RBM object, we set batch size 0. The number of hidden neurons is 100. This is just the training function, the training for loop. So whatever I'm giving at the input, I'm also setting that at the output for testing it. What comes out of the hidden neurons. So I first off sample probability of H equals to 1 given V, and then I implement the CD function 10 times, and finally I again sample H or H given V, like I told you previously, and then we call the train function, and that's. So in this case, you can see our loss is basically decreasing, and the more epochs we add, the more the loss will decrease. The loss on the test set is 0.15, so it's quite close to the from where we left off last time. So that was the first hands-on. For the second hands-on, we are basically using RBMs for digit classification. So here we are using one of the built-in data sets, which has size 8 by 8. That's available with sklearn. So it's a low digits. It's called a digits data set. And here the intuition is that I'm using the hidden layer to basically generate the data or make a prediction about the pixel, whether the pixel is going to be black or not, because that's what we are doing it. So we have to interpret the degrees of blackness on a white background. So whether the pixel is there or not, that's what we have to estimate from the Bernoulli. So the Bernoulli RBM is an inbuilt RBM that we can use directly, which is sampling from the Bernoulli distribution. So here we have to, the authors decided to increase the data, and we also have a pipeline. So we are going to have two experiments. In one, we are going to do RBM and then logistic regression, which uses the features of RBM, and one in which I'm going to just have the logistic regression separately. And then we are going to compare the performance of these two. So in this case, you can see that the pipeline basically is a module that requires, which can execute models in a sequence. So whatever comes inside the pipeline has to be a model. So first of all, what we try to do is to nudge the data set. So we try to increase the size of the data set from 4 sites by applying this convolution over it. So these are my filters, and this is my convolution operator. And then I concatenate the new data with the first data. Similarly, we do the same for the Y label, and then I return it. So now I load the digits, I nudge the data set, I do the scaling which is required, I convert that to train test split, and then I call it linear model dot logistic regression. And then I execute the RBM. So one of the models I'm using is logistic regression, the other is the RBM. Okay. So in the RBM feature classifier, first I will do RBM, then I will use those features to give to the logistic regression model. There's the pipeline. So these parameters have been discovered by grid search CV, so I'll stick with those. So first of all, we'll fit this pipeline, which is here, and then we'll fit a separate logistic regression, which is without the RBM, just a direct one, and we push it up to several iterations, 100 iterations. So this pseudo likelihood is actually the joint PDF. So you can see that it is getting more and more likely, although we still not many iterations, because 100 iterations is definitely not enough. In any case, we can print out the classification reports for both of them. So you can see that RBM followed by logistic regression has yielded 93% accuracy, while pure logistic regression has only yielded 78% accuracy. And these are the components which are extracted by RBM, the 100 components. So the third hands-on is related to the MNIST data. So it's available there. Again, we are using the Bernoulli RBM. So my batch size is 10. We just load the data and we load the next 5,000 rows. We configure the Bernoulli RBM. So we don't need to do anything else. We just call the function. And then we call RBM.fit. As this data is probably more complicated, so you can see the likelihood function started from minus 272.46, and then it starts to go down. It's 80s, then goes into 80s, 70s. You can see most of the data is now converging towards 68 and 69. So the shape of the components is 10,784 because these are the number of pixels and that is the batch size. So first we plot the original image. You can see that the data is like 6149573, etc., etc. Plot the latent component extracted by RBM. So if we just plot the component here, so you can see this does not seem really useful as far as the components are concerned. So now we call, so I think this is without the learning of RBM. We have not learned it. So we transform X and we see the shape now is 5,100. And this is what a vector, that the transform vector looks like. So here we are actually computing the hidden layer activation probabilities as equals to 1 given v equals to x. So we are just calculating that based on RBM.transform because RBM has been already trained. So I'm transforming the output with respect to the given input x. So this gives me the latent transformation. This goes up basically. And the shape is like this. We can see this. So this is what is happening at the hidden layers, in fact. And we have the score samples. So now we can use Gibbs sampling as well for this purpose. So I have RBM.Gibbs. So I can use directly Gibbs sampling. And when I do that and I plot the results, so reconstructed input images by Gibbs sampling, so you can see that it's much better. It's quite close to the original data. And when I generate new data directly from the noise, so directly from the noise, I'm generating new data using Gibbs sampling. So I again get some results, but most of them are not correct. So this generation is not happening properly. Okay, so this is the output for the random noise which we have sampled directly from Z, and when we run the RPM over that 10,000 iterations, I get Gen Z. So this is what we have sampled. So you can see that there's a bias towards 9 and 4, and like we can learning some 6s, but still you need to do more. So probably the applications of RBMs are more focused on some specific areas, probably not very much commonly used for image-based data. Okay, thanks for watching this video. Yeah.